And that final presentation is going to be given by Marco Fellin, and he'll be talking about the benefits of a pile testing program during the design phase. A perfect example that increased testing does save money. Marco, floor is yours.
Yeah,
right,
thank you. Thank you, and thanks for the opportunity to present. My name is Marco Fellin, and work for Tetra Tech out of Missoula, Montana, and I've been with a senior geotechnical engineer with Tetra Tech for 21 years. Done quite a few, worked on quite a few deep foundation projects, load testing projects throughout Montana and several other states. This particular project in Helena, Montana, had many contributors. Montana Department, it was a Montana Department of Transportation project, funded partially by the Federal Highway Administration. HDR was the lead structural design firm. Tetra Tech was involved to do the geotechnical investigation. A local testing firm, Muth Consulting, performed the lateral and uplift load testing, and Dick Anderson Constructions out of Helena, Montana, and they were contracted to do the actual pile load test program. I didn't mention Burt Minor Construction out of Seattle, and they did the PDA testing on the project. The focus of this presentation will be, the outline of this presentation will be talking about engineering aspects of deep foundation design, and then the benefits of pile load testing program, specifically during the design phase on this project. The benefits can be gained by testing during design. Next slide here. There it is. Okay. So engineering, I'm an engineer, and many of us are engineers are listening. Years ago, a senior fellow worker that I was working with asked me what engineering was, and I believe I explained to him that it was, designing something, designing a foundation, designing a building. And he explained to me that anybody could design pretty much anything. Anybody could build anything with enough time and money. And engineering was more fine-tuning that and utilizing materials more efficiently, and utilizing our judgment and coming up with a more economical design. And so the official definition of engineering is listed there, mentioning practices applied with judgment to develop ways to utilize economically the materials and forces of nature. So utilizing maybe a set amount of materials, more economically, build it more efficiently, bridge structures, bridge cross beams, whatever the case is. Especially in countries that don't have as many materials, it becomes even more important. So the focus of this presentation again will be economics, and how we can utilize our experience in engineering practice and testing to come up with a better, more economical design. As engineers, we sit down and we have a project in front of us, and we say, how do we design this foundation specifically? What have I done in the past? What would be most constructible with the technology we have in Montana or wherever we are? What diameter of pile or drill shaft should I use based on structural loads? Does the structural engineer I'm working with have a preference? Does MDT, the highway department, have a preference based on what they've used in the past and what has and hasn't worked? And then also, what are the loads that we're dealing with? What the structural engineer has heavy loads. What is his configuration of foundation? Is it a large interstate bridge? Is it a small bridge? Is it an abutment, or is it an intermediate shaft? So close consideration between structural engineers and geotechnical engineers to figure out what's going to work. And furthermore, with the bridge foundation design, what information we typically have available to us. Usually, almost always, we perform a geotechnical field investigation. Sometimes, like John said, with testing while we're doing the drilling, sometimes not. If they're auger cast piles, sometimes we're monitoring the torque. We have that data, which is really beneficial. We have logs from the drill borings. We have lab data from testing in the lab, specialized geotechnical testing. We have engineering capacity formulas. And from my experience, the formulas are based on either sands or gravels or different types of materials in different areas. And so we have to be careful with the formulas we use because, for instance, here in Montana, we have conglomerates of materials that don't sometimes apply to any of those formulas, or we have to use our engineering judgment again on what to use. Information we have available in structural loads. There's many computer programs available these days that for lateral we use a lot. InSoft is a program we use a lot that we can monitor. We can simulate lateral loading, axial loading, and use those programs for design. And then we all have past experience on what we think might work and what might not work, and that plays a big factor into a lot of designs on calibrating what we've done in the past. So with all that, with all the input from the geotechnical engineers, the structural engineers, the past experience, everything we pull together, we come up with a final product and we say, okay, here's what our best estimate is. We think in this area we're going to use 16-inch pipe piles to a depth of 30 feet. And I should note that that's an estimate. We've done the best we can as an engineer. We've got all this information, done load testing. That's an estimate. And then typically with a lot of these designs, factors of safety depending on which design method you're using. 2.5 to 3 is common for drilled shafts, and then depending on with piles, factor safety of 2 to 3. So we come up with an estimate, and then we divide that by 2 to 3 times just to come up with our allowable, which is a fair amount of factor safety. Which means if I estimate a pile length that I need of 30 feet, essentially I'm going to make it 60 or 90 feet with the factor safety. So that's a pretty big cost implication depending on the project and the amount of piles. So again, I want to just note that that's an estimate. We won't know how deep or shallow the piles, for instance, might penetrate until they're actually driven. Or a drilled shaft, a lot of times it's too expensive to test, so we don't do as much drilled shaft testing. Optimizing engineering design. One question a lot of us might not ask ourselves is, have we done a pile test load program? Have we done a drilled shaft test program? Can we afford it? What benefits would we get out of it? So again, focus of this presentation is the benefits that we could get out of that. And as engineers, we should ask ourselves more often, what can we get out of a pile or drilled shaft load testing program? What about the load testing program? During design, like I said, we do the pile test. We can do a test program during design, and it will give us a lot of information. It'll answer questions like Shashil said about, you can answer questions while you're doing the design of what problems might we have. Can we get them in that? Can we drive them that deep? Can we? How costly is it going to be? So it really answers a lot of questions, and then we can optimize. We can back calculate parameters, and we can work with the structural engineers to optimize our design and determine how we can reduce piles. The load testing during construction is beneficial as well. From my experience, if we estimate a pile depth of 30 feet and we do load testing during construction, we're verifying the capacity, but we could have a pile that goes 10 feet deeper, 15 feet deeper. We're still verifying the capacity, but we've got somewhat of a change order on our hands because, the piles went 10 feet deeper, and if we've got 300 piles, it's a fair amount of piles. So I should point out, we can use a lower factor safety by pile load testing. So even if we do it during construction, we're still getting a benefit. We're still reducing the pile length with a lesser factor of safety, but it still doesn't answer all the questions prior to construction that we could potentially eliminate some problems and costs. So I'll just present here a case study that from a project in Helena that we use this procedure of testing during the design phase. We brought it up, HDR and Tetra Tech looked at it, and we determined that the pile testing load program, even if it didn't work out to the benefit of what we thought if piles would work, we thought that at least it would answer that question, and there was such a potential cost savings that we figured that even if it didn't work out, that it was worth the effort, chancing it and saying we can spend $200,000 to potentially save a lot more. We presented it to Montana Department of Transportation. They looked it over and thought the same. They thought the benefits could be substantial if it worked out. And the Federal Highway pitched in as well and agreed to fund it. So we subcontracted I'll get into that later. The project location is in Helena. You can see there's 2 interstate bridges going over a pretty substantial set of railroad tracks and pretty long span bridge. But Helena, Montana has very complex geologic conditions. Just about anything: dredge, mining, fill, volcanic ash, conglomerate boulders. It's a lot of everything. The existing bridge was 12 spans, 800 feet long. The idea that it was seismically deficient because it was situated on spread footings. I think it was built in 1960 or so. So the idea was to replace it, get it seismically upgraded and with modern technology, modern materials, HDR was able to design it for 4 spans. Oops, sorry about that. 1 second, I got to go back here. 4 spans, and then we decided the initial idea was to put it on pile foundations. So the geotechnical goals were to design pile foundations for this bridge. That was the initial estimate by HDR, what they would prefer to use. We did an initial geotechnical investigation prior to 2011 and 12. We did 3 borings, and interesting enough, out of those 3 borings, we had one that went down all the way. This one here, DH1, it went all the way down without hitting any boulders at all. That was one of the first 3 borings, and then we had a couple others that we hit a boulder layer, this yellow layer, and here's boulders, big 3 to 5 foot diameter, and we had one in the middle that hit some boulders as well. So we had 3 to give us an idea, to give HDR an idea what we might be looking at for preliminary bridge types and foundations. Interestingly enough, we recommended drilled shafts because we said piles would refuse at a shallow layer on that boulder. We wouldn't have enough lateral capacity, wouldn't have uplift and axial. So we'd have plenty of axial, we wouldn't have enough uplift and lateral. So initially we said drilled shafts. We came back and did a full geotechnical investigation with 11 borings total, all the way across. We drilled next to the railroad tracks, and this boulder layer was prevalent throughout. This was an outlier right here. Just for whatever reason, we didn't hit any boulders, but basically the boulder layer was encountered anywhere from 20 to 75 feet in depth. 20 feet is a pretty shallow depth to support a pile on for such a large structure. So, with that, that's where the benefits of the pile testing program came in. And we said, well, if we can drive some piles at that depth and prove that they work, then it's going to be a big benefit to the project. But basically, we had clay sand material up above, which is common hill, and this big boulder layer was the question mark. And when we initially recommended drilled shafts, we figured we could get through those. We deal with them a lot in Montana. We could auger through them. We could somehow get through them, whereas we didn't think we could get piles through. But anyways, we went ahead with the pile testing program. And this is part of the drilling. You can see the boulders that were encountered in that layer. In between, there'd be some matrix of gravel and ash and cobbles, and then you'd hit another boulder. And some of these we cored through, like I said, 4 or 5 feet. So we had really good recovery. we could tell they were going to be substantial. It's not going forward. So again, we said what would be the most beneficial here. We came up with the pile testing program. Even like I said, even if we didn't, it didn't pan out that they'd work, it was going to be a benefit. I was just curious what most of you would have done in these circumstances, if you would have tried piles or drilled shafts. So maybe at the end you could let me know what the consensus was, or what other engineers would have started with as far as deep foundation type. So we drove 5 test piles across the site. We just mainly for access, we took the 2 heavy loaded intermediate foundations and we did a test pile at each bend. And interestingly enough, where that anomaly was, where the layer was deeper, we drove 3 test piles about 24 feet on average into the boulder layer. So that was kind of surprising. One of them was an H pile and 2 of them were pipe piles. And then at the other bend, the piles refused right at the boulder layer that we encountered in the geotech investigation. So from there, I made the estimate and said for our pile depths, for planned depths, I said I had to use engineering judgment again. And I said these drove a little ways into the layer. These refused at the layer. We didn't know what was happening out here because we didn't do any test piles. So I said, on average, I think I came up with an estimate of 5 feet into the boulder layer for planned pile depth, just to make sure we had enough pile. Again, these refused almost right at the layer, so we figured if we had a little extra pile, it wouldn't hurt us. Pile testing done was PDA testing for axle. We had plenty of axle, that was not a concern. We did lateral testing. We installed 2 extra piles and then used some hydraulics to push against the test pile, and then we did some uplift testing with pushing against the ground and a stack of concrete blocks. The lateral test, we used a shape accelerator inclinometer for in-place testing to monitor pile movement. Our concern was that the bottom of the pile would kick out. We wouldn't have enough depth to support the lateral load. So by using this test, we were able to monitor the pile movement at the toe during the entire loading. We could have a real-time display of what the movement was as we were loading it to see how the pile was performing. This shows the printout of the shape accelerator. It was really interesting. This is the depth of the pile of 28 feet. We took the shortest test pile of 28 feet to test. That was the most critical. That was the one that refused at the boulder layer at that one bend. So we loaded it in 25 kip increments, and every 25 kips you could see the deflection at the top, and you could also see the deflection at the bottom, which there was none for a pretty long length. And the maximum deflection was about 2 inches at the 125 kip load, and you can see from depth of about 16 feet down there was no movement, which was what we were looking for. And this load here is kind of what HDR had given us an indication that we were shooting for, to make sure we had enough lateral load to design on. So from there, we asked ourselves, did it answer our design questions? We said yes, the 16-inch diameter pipe piles will work when at that shallow depth. I back calculated the soil properties from the testing, and with that was able to give the information to HDR, and they were able to lay out their piles and optimize their design pretty efficiently. They used some of the same programs we did for lateral, so they just took our back calculated soil parameters and had real-time data, real solid data to work with instead of estimates. The end result was 372 total piles at the 10 bent locations for the northbound and southbound structures, which is a fair amount of piles. The 2 interstate bridges were constructed in 2 seasons, 1 bridge per season, and I thought I'd throw in there the joke in Montana and maybe other states is that there's 2 seasons in Montana. There's winter, which is pretty long, and then there's also construction season. And so that definitely affects us on the roads more than bridges. But anyways, they were able to construct, have enough time in each season to get these bridges constructed. And typically they do work partially through the winter here. But again, a benefit of less construction time from pile load testing helps when you don't have as much time to construct. So the end result of during construction, what we actually achieved was, I told you I estimated pile depths about 5 feet into the boulder layer all the way across, and it was somewhat unbelievable, but we had plenty of capacity at the boulder layer when we encountered it at the depth that we estimated at all locations. As soon as we hit at or near that boulder layer and started driving into it, we had plenty of capacity. And so the end result was we estimated 13,020 feet of pile, and we constructed 13,170 feet of pile, which is within 1% of our estimate, which was pretty unbelievable to me, considering the length of pile. Again, 372 piles. So they did that in about 32 days, which was about 12 piles per day. Pretty good production. I think a couple days they had up around 20 piles a day, and then a couple of slower days. The test pile program cost $200,000. That was everybody, our design time, our Tetra Tech's input, the construction, everything involved was $200,000. The pipe pile foundation estimated cost savings was, this is from HDR initially, was about $3 million. The cost for drilled shafts in Montana, on a lot of the projects we had, are sometimes $2,000 a foot, and that includes casing, more difficult drilling conditions, concrete, rebar, everything. So this initial estimate was based on 3 or 4 large diameter drilled shafts per bent versus the X number of piles. I believe we estimated drilled shafts going down to 75 feet initially. And then I think the piles initially were 40 to 50 foot in depth, if I recall. So that was a rough estimate of $3 million based on construction costs for piles and drilled shafts. The pile foundation was estimated to reduce construction by about 2 months, given that we didn't have any encountering difficulties and everything went very smoothly. There was usually on pile jobs, you have to weld a little bit. On this whole project, there was only 4 welds, and they were at a location where the piles were too high for an MSE wall, and we couldn't really see them. But that was a fair savings in time for the whole project, reducing the number of welds. The lessons learned in this project were that, as I mentioned at the beginning and during the engineering phase, the pile testing provided us with actual data that we could use to better engineer the foundation. And I think that played out in the 2 previous presentations as well, with John and Sheil, as far as getting more data up front, getting data during design, and having that in hand so that it answers a lot of questions, constructability questions. We don't have as many questions during construction. And then, like I mentioned a few times, we used engineering judgment for the depth of the piles, and we had to use judgment where we didn't have any load tests. We saved a lot of time and money, and really didn't have any delays to speak of. One of the delays they had is when they had the boulder layer, they were doing the pile driving, and the piston, the boulder layer was so hard that the piston literally just shot out of the top of the pile driving hammer, and that set them down for a few days. But that was really nothing to do with our design. It was just standard delays, but we didn't have any change orders related to the foundations at all. And in conclusion, in our minds, HDR and Tetra Tech, and MDT as well, the client, the pile testing program was definitely worth the effort and time spent. And that we, as designers, Tetra Tech we will consider it in the future, and recommend it where we can. I should point out that related to pile load testing or drilled shaft load testing, Tetra Tech also does drilled shaft load testing, and we just did a test last year. And on this project, if we had done drilled shaft load testing, we'd also have that information as well. So both foundation types, there can be a lot of benefits it's not possible always to do both drill shaft and pile load testing. I think some projects it can be done. On this one, it would have been too costly, I believe. So as designers, we went ahead with something that we thought was going to save a lot of money, and that was the short piles. So again, we will consider on future projects. I thought I'd point out in this last slide too, those piles protruding out of the ground so far they constructed an MSE wall around those piles at one of the vents. That was the most efficient construction there. So just in case you're wondering, that's what that was. But thank you for allowing us to present.